Good morning, students. Mr. Carver here. Today we're going to do section 8.2. We'll be talking about infinite series and convergence. Now, a major distinction in this chapter is the difference between a series and a sequence. So a sequence is just a sequence of numbers, as the name implies, with commas in between. So, for instance, 1, a half, a fourth, an eighth. That is just a sequence of numbers, whereas a series is the sum of the numbers in the sequence. And by the way, the notation for a sequence is just a sub n. I think it would then make sense that a series can be denoted as the sum from I equals 1 up to infinity of a sub n. And again, that is the sum of the numbers in a sequence. Now, what we'll be looking for is, in this section, as also the name implies, we'll be looking at whether a series converges. That is, whether the sum stops growing or the sum diverges. That is, it grows without bound. So, for instance, if I take a look at the numbers in that sequence right there, the question will be, does the sum, if I go from n equals 1 to infinity, and what we're looking at here is a geometric sequence. This is a sub 1, which is 1. My r is 1/2 to the n minus 1. The question is whether that sum converges or diverges. Now, the connection between 8.2 and the previous chapter, specifically section 7.8, where we did improper integrals, is essentially the same. When you look at a graph that approaches the x-axis, that is, the functional values become infinitely small. Let's say in the previous section we integrated, say, from 1 to infinity. The question was whether or not the area underneath that curve from 1 to infinity converged or diverged. Again, we essentially have the same problem in section 8.2, because now instead of having a continuous curve, I actually just have a series of functional values, dots, that give me the numbers in a sub n. And the question is whether when you add them all together, the sum stops growing. Well, you can think of it in terms of area as well, because if I think of these functional values as being the height of each one of these rectangles, the width of each rectangle being 1, well, the area is nothing more than the sum of the area of those rectangles. The width would be 1. The height would be the functional value coming from that a sub n. So essentially, I have the same problem in section 8.2 that I did in section 7.8. That is, does the sum of the areas of those rectangles grow without bound, or does it stop growing? Now, what the first half of chapter 8 is all about is investigating whether or not these sequences actually stop growing when you add them together. That is, whether the series converges or diverges. And in section 8.2, we're going to look at maybe the first 2 or 3 techniques to determine whether the numbers get small enough quickly enough in order for the sum to stop growing. So let's take a look at a couple of examples. All right, let's take the sum from I equals 1 to infinity of 1 over n minus 1 over n plus 1. Now, I just want to emphasize this. Again, this is the sequence that is a sub n, and what I'm looking at then is what happens to the behavior of the sum of all of those numbers. Now, keep in mind that you're looking at the a sub n. I think you would agree if I take a look at the limit as n goes to infinity of 1 over n minus 1 over n plus 1, I do in fact get I do get 0 minus 0. That is in fact determinate, which means the limit of that sequence, the limit as n goes to infinity of a sub n is equal to 0. That means the numbers in that sequence get infinitely small. Now, again, remember that even though the numbers get infinitely small, you don't know whether their sum stops growing or continues to grow. This is exactly like the problems in section 7.8. Really, the thing that you're investigating is whether these functional values, that is, those dots along the x-axis, get small enough quickly enough in order for the sum, that is, the series, to converge or diverge. And again, section 8.2 is investigating, or at least me showing you techniques to come to a conclusion as to whether the numbers get small enough quickly enough in order for the sum to converge, or whether they get there more slowly and the sum actually diverges. So let's get rid of this. So one of the first techniques that we're going to look at actually involves just writing out the numbers of this sequence. Well, if I'm starting here at 1, this is going to give me 1 minus a half. That would be my a sub 1. I'm then going to add that, what I get when I plug in 2. That gives me a half minus 1/3. And then I'll add that, a sub 3, which is going to be a third minus a fourth. That's not a fourth. That's a fourth. All the way and out until I get to 1 over n minus 1 over n plus 1 as n approaches infinity. So I'm adding all of those together. Well, I think that you can see as I write out these number of terms that what I get is, if I were to start actually adding these terms together, I'm going to start getting some cancellations. For instance, this negative 1/2 cancels with the positive, the negative 1/3 cancels with the 1/3, and so forth, all the way out until the end of this sequence, even though it doesn't theoretically end, all the way to the very end, negative 1 over n plus 1. And what I'm left with then is actually just the sum. So theoretically, I'm left with the first term and I'm left with the last term. If n is infinitely large, the last term is 0 and the first term is unaffected. So this sum actually converges to 1. And what that's telling you is the numbers become so small, or they behave in such a way that you get cancellations, such that the sum does stop growing and it grows to 1. Now this, I think, as the name I think is pretty apt, because when you look at this, you've got this infinitely long string of numbers that you're adding together, and then through cancellation it actually telescopes down to a few finite terms. This is called a telescoping series. And that, again, the telescoping series involves actually just writing out the terms, looking for cancellations, and determining which terms are left at the end. Now, I'll show you another example here. Sometimes they are hidden. And as you might be able to see in this example right here, if I take the sum from 1 to infinity, 1 over 2n plus 1 times 2n plus 3, that quantity product there, if I actually started writing out the terms, I would get absolutely no cancellations. Well, the problems in this section are such that if you were to actually break up these terms, or this fraction rather, that is, decompose it into its component fractions, you in fact will get some cancellations, and that is going to involve, as you might expect, partial fractions. And that process is exactly the same as the one that we went through in Chapter 7. I'm going to skip over all that algebra. Suffice it to say that A turns out to be positive 1/2, and B, that is capital A, and capital B turns out to be negative 1/2. Again, if you're looking for how this all works, get a common denominator, pick convenient values of x, solve for A and B. In the interest of saving some time, again, I'm skipping all of that. Now what that means is that this sum, or this series, starts at 1, goes to infinity, and I'm going to get 1/2 over 2n plus 1 minus 1/2 times 1 over 2n plus 3. All right, now to make the numbers maybe just a bit easier, I think what I'll do is take a 1/2 out in front of everything and just get rid of these 2's here. Make the numbers maybe a slightly more manageable. All right, and now here's what I'm going to do, just like I did in the previous example. I'm just going to go through and calculate a sub 1. And a sub 1 in this case turns out to be 1/3 minus a 5th. Add that then to a sub 2, which is going to be a 5th minus 1/7. I'll add that to a sub 3, which is going to be a 7th minus a 9th, all the way out to the end. And you can see that as n gets infinitely large, these numbers do go to 0, which means that the infinite series has a chance of convergence. Remember, the numbers in the sequence have to get infinitely small in order for the sum of the area to potentially stop growing. Again, that's what we're investigating here. And once you've seen enough of a pattern to determine what the cancellations are, you can then start canceling them out. This actually converges to 1/3 times 1/2. The infinite sum actually is 1/6. Don't forget the 1/2 out to the front. So again, that infinite series converges. All right, one of the more common series that we talked about early on, actually in section 8.1 and last year, also the year before, were geometric series. So let's talk about those now. Now, as opposed to a geometric sequence, which is what we talked about in section 8.1, so if I take a look at just like a generic geometric series, I'll start at 1, go to infinity. This gives me the first number in the sequence times my ratio to the n minus 1. Incidentally, they can also be written as the infinite series from n equals 0 to n of a sub 1 times r to the n. Now, if we're dealing with geometric series, we actually have a test to tell us whether the actual series converges or diverges. This is called the geometric series test. And the geometric series test looks something like this, given a geometric series with a ratio of r. If the absolute value of the ratio falls between 0 and 1, the series converges to the sum of, and I'll go ahead and write this fully out here. This is the sum from n equals 0 to infinity of a sub 1 times r to the n. This converges to a sub 1 over 1 minus r. Now, I should mention, my notation's off just slightly. It's technically could be a sub 1, could be a sub 0. Don't get too caught up in the a sub 1 there. That is really just the first term of the sequence. And then, of course, r is your ratio. Now, this formula only works, again, if r falls between, the absolute value of r, rather, falls between 0 and 1. So we'll take a look at a quick example here. Something maybe that looks like this. The question would be, well, does this series converge or diverge? It's helpful to recognize that this is, in fact, a geometric sequence, or a series, rather, since they're being added together. and you have a common ratio of 1/3 every single time. That's necessary in order to qualify it. Actually, by definition, that's what makes a geometric series. All right, so really, here's what we're adding together. You've got n equals 1 to infinity. I've got 2 times 1/3 to the n minus 1 power. My r here, the absolute value of that r, definitely falls between 0 and 1. So you would say that this converges by the geometric series test, since your r falls between 0 and 1. And it also converges to we'll call this S sub infinity, that is the infinite sum. You've got the first term in the sequence, that is 2 over 1 minus 1/3, which is 2 over 2/3. The answer turns out to be 3. So the infinite sum actually is 3. And again, you know it converges because of this statement and this test. I'd like you to cite both of them on tests and quizzes. You are using the geometric series test. Due to the fact that your r falls between 0 and 1, that is, your absolute value of r falls between 0 and 1, you know it converges by the geometric series test, and it converges to that value right there. All right, now notation is key for the geometric series test. So let me give you an example of one that might be slightly different. Let's say I've got the sum from n equals, well, let's do 1 to the infinity, 2 to the 3/5 to the nth power. And I ask you whether this converges or diverges. You would say, hey, as r is equal to 3/5, that series will converge by the geometric series test. That is your rationale. And it will converge to your S sub infinity, again, as a sub 1. And you think about a sub 1 as being the first term in this sequence. But you have to look at the notation, right? So if I take 1 and I plug it in there, what I get is 2 times 3/5 to the first. That is going to be 6/5 as the first term that I'm multiplying together, all over 1 minus my r, which is 3/5. This is going to give me 6/5 over 2/5. The answer will be 3. I guess I should also mention that they don't always converge to 3, but these two certainly did. Just the notation is what I'm trying to point out in this example. All right. Now in section 8.2, I've got one final test that we need to talk about, and it is the nth term test. And the nth term test says this: if the sequence, and this is a sub n, remember that's the notation we use for sequences, does not converge to 0, then the series diverges. If the sequence a sub n does not converge to 0, then the series diverges. Let's take a look at a couple of examples. How about this one? You've got the sum from n equals 1 to infinity. We will do like something like let's use 2n squared plus 1 all over 5n squared plus n plus 1. This is going to take us all the way back to chapter 7 again. When you start these problems, you must first investigate the behavior of a sub n because of this test. If I take a look rather at the limit as n goes to infinity of a sub n, this is 2n squared plus 1 all over 5n squared plus n plus 1. What I get is an indeterminate statement, that is infinity over infinity. So I use L'Hopital's rule. And I'm going to get 4n plus 0 all over 10n plus 1. Still indeterminate. I'm going to use L'Hopital's rule again. This gives me 4 over 10. That means my sequence goes to 2/5. So this series then will diverge by the nth term test. Now, I want you to state the test that you're using. I also want you to show me the supporting work that leads you to this conclusion. This diverges by the nth term test, because think about this. These numbers do not get infinitely small. What they do is they get closer and closer and closer to 2/5. So what I'm doing is adding an infinite number of 2/5 together. And as you know, with enough time and enough 2/5, it ends up being a very large number. Taking a look at another one here. Let's say that I've got a geometric sequence. Let's do 5 times 3/2 to the n. Again, this is a geometric sequence, series rather, because of my r here. A constant r leads me from one term to the other. However, in this case, my r is greater than 1. R is equal to 3/2, which means if I take the limit as n goes to infinity of just the sequence, this is 3/2 to the n, what I'm going to get is infinity. These numbers get larger and larger and larger. I'm multiplying them by 1.5 every single time. It goes to infinity. Since the limit as n goes to infinity of my sequence, again, this is a sub n, is not equal to 0. That means the series of a sub n diverges by the nth term test. Now, put this in your notes, please. The nth term test, this test right here, is used only to show divergence. It cannot show convergence. Let me give you a quick example. Let's say I have the sum from n equals 1 to infinity of 1 over n. I don't yet have a test to show you for this, but show you how this works. But if you think about it in terms of area, 1 over x dx, and I go from 1 all the way to, say, a, right? I take the limit as a goes to infinity. What I get then is the natural log of the absolute value of x going from 1 to a. I get the natural log of hugeness minus the natural log of 1. Taking again the limit as a goes to infinity. I think you would agree that this is infinity minus 0. Now we're going to come back to this in a future section, but I think you would agree that if the area of 1 over x from 1 to infinity is in fact infinite, it diverges, then the sum of these rectangles would also diverge. The fact that I'm undercounting it by these little like semi-triangular shapes doesn't really matter. The sum of those rectangles will also be infinite, so this thing is going to diverge. However, this goes to 0. The limit as n goes to infinity of 1 over n is 0. Yet, when I add them all together, it diverges. Again, this goes back to the concept that it's all about how quickly these numbers approach 0 that determines whether the sum actually stops growing or not. So again, if we look back at the nth term test, it can only show divergence. The only conclusion I can come to is that if the numbers do not get infinitely small, the sum will definitely not stop growing. The sum will diverge. All right, people, I think I've gone on long enough. Hopefully this will get you through section 8.2. I'll certainly help you as much as I can. Thanks much.